I'm really happy to introduce our 12th Frith Prize lecturer, Dr. Tom Arthur. The Frith Prize is given to a scholar at the first part of their career who's produced an exceptional body of work in their PhD thesis. Tom completed his PhD last year at the University of Exeter with a thesis titled Sensory Motor Differences in Autism, an Evaluation of Potential Mechanisms. In his thesis, Tom developed a range of novel virtual reality paradigms to test hypotheses about predictive processing in autism. And the nomination from his external examiner talked about the technical challenge and the high degree of imagination in these paradigms. And unsurprisingly, Tom's PhD led to 5 published papers, all the more impressive given that this work was undertaken during the pandemic. So I'm delighted to turn over to you, Tom, and we're really excited to hear about your work.
Well, thank you so much. Yeah, thank you so much, and thank you so much to everyone for sticking around for this talk. I'm really, really honoured to have this award. So today what I'm going to talk to everyone about is my PhD, which I completed just over a year ago now. Specifically, as we just talked about, my PhD was looking at sensory motor differences in autism. So for the next half an hour, 45 minutes or so, I'm going to hopefully give you guys a bit of an overview and a background about this topic before discussing the sort of journey I went on during my PhD and some of the potentially new findings that we think we've contributed to this field. At the end, I'm hopefully going to have a bit of time to talk about some of the potential applications of these findings and some of the future work that we're hoping to do in this field and that we've started to do. So I'm sure everyone here is familiar with autism. Autism is one of the most commonly diagnosed neurodevelopmental conditions. It's diagnosed in approximately 1 to 2% of individuals, according to differences in social interaction, communication, and behaviour. Now, for the purposes of this presentation, I'll be mostly using identity first language, so using things like saying things like autistic person, autistic community, and that's following some really excellent research that's been done in the last few years in global populations and specifically within the UK. Where working with autistic people, these researchers have been able to identify the sort of language preferences from within the neurodivergent community. So autism is generally diagnosed according to differences in these 3 areas, and a lot of research has generally been done in these 3 areas. However, there's a lot of other difficulties and differences that autistic people can face in their day-to-day lives that are much less well researched. So in particular, there's a growing body of evidence that suggests that most autistic people experience sensory motor difficulties. So things like clumsiness, things like difficulties with hand-eye coordination, difficulties with balance, differences in sensory integration during movement-based tasks, and difficulties performing and learning movement-related skills, which can impact on things like independence, daily living skills, and health-related quality of life. So there's an emerging sort of theme that's starting to, as I say, emerge in research that suggests that these difficulties are potentially a core feature of autism. However, there's a real lack of research in this area, and there's a real lack of understanding about why these differences might occur. And in particular, there's a real lack of evidence-based programs and support for autistic people that can help them manage these difficulties in their day-to-day lives. So the broad aims of my PhD were to try and develop our understanding about why these difficulties might be experienced by autistic people, with the view of hopefully kick-starting this development of future evidence-based support and developing novel strategies that can help autistic people manage these sensory motor difficulties in their day-to-day lives. So when I talk about sensory motor control, I'm talking about this dynamic, complex interaction between sensory signals, between neuromuscular outputs, that's all occurring during bodily movements. And you can see these quite complicated looking diagrams with a lot of words that people here will be more or less familiar with. And for those of you from this field, lots of people will know that some of these sort of key areas here have been maybe associated with differences in autistic populations. So in particular, the cerebellum, for example, there's a lot of research suggesting that autistic people may have some difficulties. However, the research in this area is relatively varied. Okay, so the differences, for example, in the cerebellum are by no means uniform, and it's becoming widely sort of accepted that autism is likely to result from various different etiologies. And autistic people have a variety of different preferences, variety of different behavioural differences that are shown. And this emphasised, sort of at the start of my PhD, we wanted to maybe look at the sensory motor system from more of a sort of functional perspective. So we used this model by Michael Land that's heavily used in cognitive psychology and sports science. And we specifically, at the start of my sort of literature review, I tried to sort of look at evidence from within each of these areas to try and understand a little bit about what mechanisms might be causing differences in sensory motor control. And what we found when looking at this evidence is that differences in sensory motor control have been shown in relation to numerous different systems and functions. So autistic people show differences in action planning, differences in sensory perception. So for example, autistic people have been shown to be less susceptible to certain visual illusions. We know that some autistic people experience differences in their sensory sampling behaviours. So for example, they might show atypical eye movements, they might fixate on different things, in particular in sort of social settings. And there's been some evidence that suggests that autistic people show atypical motor kinematics, differences in EMG activity during sensory motor tasks. So essentially what this early sort of deep dive into the literature was showing was that differences exist across multiple different sensory motor systems, multiple different functions and networks. And we needed to try and look at mechanisms that could explain differences across lots of different levels. We needed to take a holistic approach in doing this. So this was really, what then became really of interest of us was some of these sort of predictive theories of autism that have emerged in the last decade or so. So for those of you that maybe are not familiar with some of these theories, there was a number, sort of, as I say, 10 years or so ago, there was an increase in a number of high-profile theories of autism that argue that various difficulties that autistic people face might be related to, for example, difficulties making or using predictions. These theories were then framed using Bayesian explanations and neurocomputational models. So this work by Elizabeth Pellicano and David Burr suggested that autistic people are maybe less likely to use prior expectations, or prior expectations are attenuated compared to neurotypical individuals. And this can explain lots of different features of autistic perception and action. We then saw we've then seen growing research that has attempted to explain this using predictive coding and sort of neurophysiologically based models of the brain. And some of this recent work by Rebecca Lawson and Carl Friston has attempted to explain this then using hierarchical models. So, for example, this theory here would suggest that autistic people don't necessarily have any sort of impairments in the ability to use predictions. However, the way in which predictions are adjusted, the way in which they're weighted and scaled according to things like uncertainty and environmental stability might be different. So the reason that these were really interesting for us is because what these were providing was a mechanism that can affect lots of different sensory motor systems, lots of different sensory motor functions. If we go back to this model I talked about a second ago, we know that predictions, there's lots of evidence or lots of theories that suggest that our ability to spot this little sort of green dot of light in a very noisy visual workspace is aided or guided by predictions. There's a growing body of evidence and a large body of evidence that suggests that and that has shown that generally when performing sensory motor tasks like hitting a ball in tennis, we tend to use predictions to guide our eye movements. So in particular, what you tend to see in these sort of tasks is that the eyes tend to sort of skip ahead of the ball based on where people predict it's going to be in the future. And finally, we know that predictions are really important in determining the specific outputs that are produced by our neuromuscular systems. So this was really interesting to us. We were really interested in exploring this link between autism, prediction, and sensory motor control. We wanted to do this in a holistic way, but we wanted to do this in a way that was still naturalistic. We wanted to look at tasks that weren't sort of unnecessarily constrained or weren't constrained to one of these specific systems. And so at the start of my PhD, the specific type of task that I was interested in was the sort of daily living skill of just picking up things and interacting with objects. So if you think of all the different things you've interacted with today, you think of picking up things, lifting things, grasping things. These are things we're doing hundreds, if not thousands of times a day. And so we got participants into the lab and we looked at how they picked up, how they grasped, how they lifted objects. We measured their hand movements, their eye movements and the fingertip forces that they use to pick up, grasp and lift the objects. And what we could do in this sort of task is we could isolate a number of prediction-related measures. So in the first study of my PhD, we measured a lot of different prediction-related outcomes, and we looked at their association with self-reported autistic-like traits, which were measured using the 50-item AQ. Now, once we'd identified which measures were sensitive and which measures might be related to certain autistic-like traits, we then followed this up with a more refined between-group analysis, where we compared autistic individuals and neurotypical individuals who are matched according to age, gender, and handedness. So what specific things did we look at and what specific things did we find? Well, before participants lifted any of the objects, we presented them with these 3 objects and asked them to predict how heavy they were likely to be. So before they'd lifted them, before they'd interacted them, what did they expect? And what we found, unsurprisingly, both neurotypical and autistic individuals predicted or made expectations that the larger object was likely to weigh more than the smaller one. And you can see here that there's no differences whatsoever really that are apparent between groups. But unbeknown to the participants, 3 of the objects in this object lifting protocol were exactly the same weight. So we could isolate some specific expectation-related outcomes that might emerge in their sensory motor behavior. In particular, if we focus on the fingertip forces that we use to grip and lift the object, what we saw in our neurotypical group is what has been shown in numerous different studies. Essentially, what we have here on the y-axis is peak grip force rate. This is the rate at which the object was gripped by participants. And what we can see here on trial 1 is that the larger, heavier looking object is being gripped with higher force rates than the smaller one. So it's important to remind you guys here that these objects are exactly the same weight. So this is something that's directly related to prior expectations. And you can see that then by trial 2, 3, 4, and through to 8, that as participants become more familiar with the objects, that these differences become much smaller. They update their predictions, they update their prior expectations. So what's really interesting here is that autistic participants showed very similar prediction-related profiles over time. In fact, when we looked at numerous different outcomes, we found that the ability to make and or use predictions at a sensory motor level was unrelated to autistic-like traits, and it was not significantly different between autistic and neurotypical groups. This same pattern of evidence was shown when we looked specifically at prediction-related measures that were obtained from eye tracking, and some prediction-related measures that were taken from participants' motor kinematics. So what we're seeing here is that the ability to make and or use predictions was not necessarily different in autistic individuals. However, there were some, when we started to look at some of the sort of individual plots and some of the individual graphs, we did see that on some specific trials there did appear to be some prediction-related effects that warranted a little bit of analysis. So we conducted a follow-up exploratory analysis, and I do want to emphasize this was exploratory. We sort of followed this up once we observed some of that earlier data. And we specifically wanted to look at the role of uncertainty that it might have on some of these effects that we've been looking at. And to specifically look at uncertainty, we wanted to look at sensory sampling behaviors, as researchers suggested that things like eye movements are really sensitive to changes in environmental stability and uncertainty. So what we saw, this is a baseline trial and a neurotypical participant lifting an object. And what we can see, this little green dot is what they're looking at. And this participant is showing essentially a very low search rate. So they are only really fixating on 2 things here. They're fixating on the handle that they're picking the object up with and the platform that they're putting it down on. Now in this baseline trial, the objects, they were lifting a medium-sized object that was weighted in a very sort of normal way. And participants lifted the same object 5 times. So by the time they got to their 2nd, 3rd, 4th, and 5th trial, which are the ones we averaged, they knew exactly how heavy that object was, and they'd interacted it with before. So this gave us a sort of comparison, control, predictable stimuli. We then compared it to uncertain lifts. So these were the first lifts of each different size object when they had no idea how much the object would weigh. And as I said earlier, these objects were sort of unexpectedly weighted. And what you can see here is that search rate has basically increased. So the participant is looking at a higher number of fixation locations. You can see that they're sampling the object much more before they pick it up and when they lift it. And these fixations are relatively short in duration. So essentially what we're showing here is context-sensitive changes in gaze control. Essentially, what I've just talked about there, search rate is increasing in our neurotypical participants between the baseline stable trials and the uncertain, unexpected lifting trials. And this makes sense from a neurocomputational perspective or an active inference perspective, because if the world around you is more uncertain and your prior expectations more uncertain, your brain's sort of saying, give me more information, give me information from sensory feedback. However, what we found in our autistic participants is that these changes weren't being shown whatsoever, and we saw no significant differences. So this is something that, as I say, though, was exploratory. We needed to look at these things a little bit more directly. And so at this point, our conclusions from our object lifting studies were that actually the sort of most important finding here from our perspective was that numerous prediction and numerous predictive control functions do not appear to be any different in autistic individuals. We do see some differences in sensory motor prediction that occur in certain conditions and certain trials. However, clearly we need to do some more research looking at the role of the environment, looking at things like uncertainty and how predictions are scaled and updated according to environmental factors. So to do this is where we turn towards virtual reality. What virtual reality allows us to do is to systematically control everything that occurs in somebody's environment. We developed a task using some previous research by Mary Hayhoe, Gabriel Diaz, and David Mann. And basically, you can see here, participants were presented with a task. They were required to hit a ball back towards a target whilst we track their hand and eye movements. What you can see in this video is these little green dots is where the person is looking on a given trial. Obviously, participants wouldn't normally see them. And hopefully what you can also see here is this ball is looking like and behaving just like a tennis ball does in the real world. And so this is a nice advantage of VR, right? So it means that we can control the exact trajectory, the exact speed, and we can make it highly predictable and highly systematic over time and highly reliable. But also what VR allows us to do is to create highly unexpected, unpredictable outcomes. So this quite amusing example here is an example where a participant is faced with a really, really bouncy ball, an unexpectedly bouncy ball. And the bit I absolutely love about this is what you see sort of now as they turn around and look back in complete sort of confusion as to what's just happened. But actually the reason the participants sort of interacting in this way is relatively unsurprising. This ball is bouncing with an even higher level of elasticity than even those like rubber bouncy balls you used to get as a child. So this is like nothing you'd normally see in the real world. This violates all sort of prior experience and prior expectations that somebody might obtain. And so what we could do is we could give participants expected trials and we could give them unexpected trials. And we could vary how we presented these trials over time to create different uncertainty and stability conditions. What we have up here is basically these blue dots is a trial where you've got a normal ball. These red dots is a trial where you've got a bouncy ball. And we had first, these conditions were counterbalanced, but we had our stable conditions. So in these conditions, the probability of getting a normal or bouncy ball remained predictable over time. You can see in this example, we have 3 normal balls, 3 bouncy balls, 3 normal balls, and this serial order repeats itself. Alternatively, we also had a volatile block of trials where the probability of getting a normal or bouncy ball was unpredictably changeable over time. So you can see here at the start of this volatile block, there's sort of an equal number there of blue and red dots. You can see in the middle that there's a sort of like really high number of blue dots and normal balls. So basically we were creating an environment where predictions were unreliable and predictions and probabilities were changing over time. Crucially though, we had the same number of trials in each block. We had the same number of normal balls, the same number of bouncy balls. We had the exact sort of same overall probability of facing a normal or bouncy ball. We had order matched trials at the end, and we had identical performance feedback. So when participants would hit the ball, it would sort of pop and you wouldn't be able to see where it's gone. So what do we find here? Well, firstly, we just looked at general task performance. What we have on the y-axis is interception rate. This is just simply the proportion of balls that were successfully hit by participants when they were performing the tennis task. And what you can see is that generally, you can see this isn't a particularly sensitive measure at all. As I say, we're just looking at whether the ball hit the racket. And we can see there's some ceiling effects. But generally, we did see that autistic participants were showing some performance difficulties and sensory motor difficulties here. But these appeared to be much more pronounced in the volatile task conditions. So when ball bounciness was unpredictably changeable over time. What you can also see there, though, is that there's an awful lot of variability that exists, and this is something that we wanted to look at in a little bit more detail. But first, what we clearly needed to do was look at a little bit more sensitive measures that might be related to sensory motor performance. So to do this, we looked at some measures relating to swing kinematics and hand kinematics. We looked at hand movements as indexed by the sort of controller position. And we extracted some key measures. I sort of buried my head in the sports science literature and looked at some tennis-related research, at some sort of key variables that might be related to expertise or prediction in these sort of tasks. And to give a brief overview of these sort of findings, we found that generally autistic participants used swing actions that were slower and closer to the body. This is generally associated with more novice-like movement patterns in the tennis literature. We also found that the range of motion in a swing tended to be highly sensitive to environmental conditions. So what we're seeing here is under the volatile conditions, swing range of motion was reduced. The degrees of freedom in someone's movement was reduced. And again, this sort of makes sense from an active inference perspective. If the world around you is more uncertain, you can actively reduce some sources of uncertainty by making the movement a little bit shorter, a little bit less complex. But we did see that autistic individuals had generally lower swing ranges of motion, so they were sort of interacting with the environment like it was constantly uncertain or unstable. But we wanted to look at these predictions a little bit more directly in this task, and we designed an experimental task here where we thought we'd be able to do this on a sort of trial-by-trial basis. So what we have here is, again, we sort of turn to eye tracking. What we have here is gaze position. This is basically elevation. So if you're higher up on this graph, you're looking closer to the ceiling. If you're lower on this graph, you're looking sort of closer to the floor. And hopefully what you guys are instantly thinking is how similar these two lines are, sorry. We can see that autistic participants were using very, very similar strategies to neurotypical individuals overall. And these strategies were directly related to prediction. So to begin with, both groups tended to closely sort of track the ball and get information about its sort of early flight trajectory. But then, as I alluded to earlier, what's really interesting in these sort of tasks is people predictively shift their gaze ahead of the ball based on where they predict it's going to be in the future. Now, what lots of previous studies had shown, and what our data also showed, is that participants tend to look slightly above the floor based on where they think it might be after it's bounced. So what this was doing in this specific task we designed here is if people thought the ball was likely to be more bouncy, they tended to look higher up. If they thought the ball was going to be less bouncy, they tended to look lower down. And so we could look at the location of this predictive fixation to extract sort of trial-by-trial expectations in relation to ball bounciness. Once the ball then catches up with this sort of predictive fixation, what we then see is that participants try to track it quite closely as it approaches their racket. And so if we go back to these figures on the left here, what you can see is that generally, as I said earlier, autistic participants were using very similar overall strategies, and we found that they were clearly using predictions to guide their gaze behaviours and gaze responses. But what you're also probably noticing is this sort of separation between the lines at the time that the ball is bouncing. So this was an effect that was pretty reliable and that we looked at that basically suggested that autistic people were increasingly preparing for these unexpectedly bouncy balls. We also found that autistic participants the location of these predictive fixations were more variable in our autistic participant group. So the net effect of this is that ultimately autistic participants were then less surprised when they were presented with these unexpectedly bouncy balls. And we were able to directly measure this when looking at participants sort of like post-bounce tracking profiles on each trial. So the results that we found here actually directly replicate and support some of the previous findings that have been shown in more sort of psychophysical experiments by Rebecca Lawson and colleagues at the University of Cambridge. And they suggest that, once again, that the ability to make and use predictions is not different in autism, but the way in which predictions are being updated according to error, according to unexpectedness, uncertainty, and volatility might be different. So overall, what our results were suggesting is that autistic people do maybe struggle with more uncertain and unstable environments, and that these difficulties appear to co-occur and do also correlate with differences in visual sampling behaviour. Once again, I want to sort of reiterate that contrary to a number of the sort of early predictive theories of autism, we don't see any generic differences in how predictions are made and used in autistic participants. But this sort of key question was sort of popping out at this stage of our research. How can we make sensory environments more predictable for autistic people? And the reason this key question seemed to be important for us, if we go back to our performance data, is that actually under the more stable, predictable environment, we are seeing much less pronounced sensory motor difficulties. So the final study in my PhD just aimed to try and address this question of how can we make sensory motor environments, particularly the more sort of volatile and unstable ones, more predictable for autistic people. And to do this, we adapted our racquetball VR task. So what you can see here is on the wall, we're providing an explicit cue about whether a ball is likely to be low or high in bounciness. We also, to indicate that the probabilities of getting a normal or bouncy ball were changing over time, we physically changed the room or the level that they were in. So we sort of transported them into a different room, and at the start of each game level, we presented some of these Hawkeye cues, which showed how many balls would be normal, how many balls would be bouncy at each level. And participants would sort of work through this. We did some manipulation checks, and autistic participants and non-autistic participants appeared to understand these cues and appeared to use them at least instantly in their behaviour. So if we gave participants a cue that said that they were likely to get a really bouncy ball on the next trial, we tended to see that all participants looked higher up on that next trial, whether they were autistic or non-autistic. So what we did is we presented sort of cued and non-cued blocks of trials. They had exactly the same order, exactly the same balls in each one, and they were volatile, like in my last study, such that so they were unpredictably changeable, as these were the conditions that we found autistic people can sometimes find more difficult. But what we found is that autistic sensory motor differences were shown still in both non-cued and cued conditions. The explicit cues did not improve or affect task performance in autistic individuals. So simply providing this explicit prior information about how bouncy a ball was likely to be did not affect their performance levels. It also didn't seem to have much effects on their sensory motor prediction that we indexed again using these sort of predictive fixation locations. So what we have on the y-axis here is just basically how high up this predictive fixation is. And we can see here that the explicit cues did not affect autistic sensory motor and predictive gaze behaviours in this task. And this is contrary to the fact that actually we did see some differences in neurotypical profiles. So these results are really, we do think these results are really important because they show that autistic people do maybe struggle with some uncertain and unstable sensory motor environments, and that whereas like in some other domains, you think of like education, you think of social situations, sometimes providing prior explicit information in advance can help alleviate those difficulties. Actually, when you're interacting in sort of very dynamic, unstable environments, it does suggest that just simply providing advanced information may not necessarily be helpful. So overall, we think that my PhD can we think there's some sort of key conclusions that can be extracted from the PhD that might be important for theory and practical applications. We think that a sort of key theme that's emerged is that predictive sensory motor control is atypical in some autistic people, but only under certain environmental conditions. So contrary to some of the high-profile theories that have emerged in the field of autism in recent years, the generic ability to make and or use predictions does not appear to be affected. However, we do think that how predictions are scaled, how prediction errors are weighted, and how these things are adjusted according to things like uncertainty and environmental instability might be different in autistic people. And this does support some of the more recent theories produced by Rebecca Lawson at the University of Cambridge. And I do recommend, she's drawn some really nice links between some of these neurocomputational differences and how these might be related to certain neurophysiological mechanisms. And so I do recommend, if you are interested in that, to read some of this work. But what we were really interested in was this sort of practical element of it. And we do think that our research has shown that we need to be supporting autistic people and helping them navigate with uncertain, unpredictable sensory motor environments. So as the final study sort of showed, just simply providing information might not always be effective. We need to make sort of direct environmental accommodations. We need to directly make tasks more predictable in nature. Or there's some sensory-motor environments that are unfortunately always going to have elements of unpredictability and uncertainty. And so we need to be supporting autistic people and helping them develop strategies that can help navigate these areas. So to finish, I just wanted to briefly discuss some of the potential applications and ideas that we have in this area and where we're hoping to take this work moving forward. So perhaps unsurprisingly, one area we're really interested in is this idea of virtual reality and how it can be used specifically to help autistic people. There we go. So some of the work I've been doing in the last year or so has been trying to sort of develop our capabilities within virtual reality. Key findings that sort of emerged from our PhD that are maybe less direct or more indirect, we found that actually, and hopefully I've sort of shown to you here, that virtual reality can allow us to directly affect things like predictability in an environment, uncertainty in an environment, and we can control these in a way that you could never necessarily dream of in a lot of real-world settings. And so a lot of the work I've been doing recently has been trying to work out how we can measure things like eye movements and stuff in real time and feed them back into the virtual reality so that we can provide environmental accommodations for autistic people. And we can do this on an individual by individual basis. So based on somebody's eye tracking behaviors and specific sensory motor response, we can individualize or tailor things like a learning environment or a performance environment according to their predictions or their learning style or some of these factors. So here, one of the things I've done in a recent short-term project funded by the Wellcome Trust is I've looked at, so Dr. David Harris presented some work yesterday on a version of this racquetball task where the ball fires out of either the right-hand side or the left-hand side, and you can manipulate the probabilities and uncertainty of the ball coming out of either side. But what this specific version of the task is doing is it's adaptive. So if somebody is predicting, this example, the participant is predicting that the ball's likely to come out of the left-hand side, and they were looking at that side, and the ball is then, we present an unexpected outcome. So this is a relatively simple, this isn't particularly sophisticated, this is a relatively simple thing. We're basically creating an unexpected cue based on someone's predictive gaze behaviors. But hopefully what I've shown in studies 3 and 4 is that if we can manipulate the predictability or the unexpectedness of a single thing, we can also control things like uncertainty and stability of an environment. And if we're doing this on an individual basis, then we can control the predictability of an environment based on an individual's response. So this is something that we now think is at a level where we're really interested in applying it in other potential actually sort of support strategies and learning programs for autistic people. Another thing that I've been working on the last year that we think is particularly important now is, as this work moves forward, is engaging and working with autistic people. So I was really lucky to co-organise and co-run a workshop just a couple of weeks ago at the Centre for Applied Autism Research in Bath, where we got lots of participants from the local autistic community to come in, and we sat through and we talked through a number of different things in relation to what research should be done, how research should be done, what adjustments could be made, what topics are important. And this is something that, if I link back to some of the VR stuff, I think is really, really important. If we're going to build new tools, we should be building these with autistic people. Autistic people should be involved in the design process and helping us develop effective programs in the future. And then one area that did pop up at the workshop that might be potentially useful and that we're starting to now become really interested in is potentially using VR as a way of helping autistic people with learning to drive, for example. So this is something that was raised by a lot of autistic people as being something that could be really valuable. Not just at this workshop, but a whole body of evidence has shown that autistic people really want us. I've just presented some research that's specifically been looking at tennis, but actually, whilst there are lots of autistic people that would like us to improve tennis skills, actually there's lots of things that autistic people would rather I'm spending my time researching, such as improving daily living skills, improving independence, and these things have been highlighted as really important in some really good work, in particular by Autistica. And so we know that driving is directly related to things like independence, right? And there's a growing body of research has shown that autistic people are less likely to learn to drive, they're less likely to pass their test, and that sensory motor difficulties are a potential barrier in this process. And so one thing I'm now really looking forward to hopefully getting my teeth into is applying some of the findings from my PhD. Things like predictability could really nicely feed into something like learning to drive. using some of the technology that I've just talked about, things like adaptive VR, and also working with autistic people to develop effective skills in this area. But another thing that we've potentially been that we've also been working on in the last year or so, that was obviously more of a sort of direct consequence. You could see a sort of key path, and obviously I'm hoping to pursue that directly. But we've also been working with service providers to help apply some of the research and some of the key findings that we think emerged from the PhD. And one of the examples of this that I just want to mention, A, because of VR, and B, because it's specifically working with Derriford Hospital just up the road here, is we've been working with Syneon Immersive Training, a local company here in the Southwest, who've developed a tool that can help people who are anxious about going into an MRI scanner. So the NHS spends a lot of money each year on scans where people move, and so the scans are therefore poor quality, or people maybe aren't able to show up to their appointment because they're extremely anxious about going into a scanner. And for those of you that have had an MRI scan will probably relate to this. And so what this sort of VR application allows patients to do is they're able to familiarize themselves. They can, for example, in the sort of safe space and the comfort of their own home, they can experience an MRI scanner. They can practice certain skills for dealing with this potentially anxious stimuli. And I've been specifically working the NHS autism service at Derriford have reached out to Syneon Training, and I've been having some discussions with them about specifically how this could be used for autistic people. Obviously, you can see the potential links here, potentially with things like predictability in the environment, and also how we can maybe adapt this specifically to suit the individual sensory preferences and needs of autistic individuals. So finally, I'd just like to say a massive, massive thank you to my supervisors, my collaborators on the project, and also obviously the funders that allowed this research to take place. And I'd like to say thank you very much to everyone here for listening to the talk, and hopefully we have some time for some questions.
Thank you, Tom, for putting so much into that. And I think, the work is really imaginative, but I really appreciated, how you talked about the applications and the way that you're trying to develop the paradigms to actually improve the lives of autistic people. So I'm sure that there's lots of questions. Would anyone like to begin? Yes.
Yeah, I love that actually. Really, really enjoyed it, and I really liked seeing that sort of neurocomputation approach applied in a sort of naturalistic, visual motor setting rather than people judging the ball patches and what have you. My question is the sort of connection between Rebecca Lawson's results and yours. So, the title of her paper is that people with autism overestimate the volatility of the environment. Well, I'm struggling to remember how they concluded that from their data. But wouldn't you think then in yours that they would have an advantage in a more volatile environment and not a disadvantage? How does that work to your mind?
Yeah, great question. So firstly, Rebecca Lawson's work, how they're sort of able to come to those conclusions is they were particularly interested with those surprise responses. And so if you have reduced surprise when you're given an unexpected event, that's how neurotypical individuals typically deal with sort of volatile environments. She uses a really nice analogy here that I'm going to just steal for this purpose, but I've obviously cited her here. So she used the analogy of coming into the sock drawer in the morning when you sort of wake up. That's a highly predictable environment, right? So every morning, I normally do it in the dark whilst my partner's still asleep. Quickly put your hands in, get a sock out, and you make this expectation that within that sock drawer, there is going to be some socks. They're nice and soft things that you can quickly put your hands in, grab, and leave quickly. That's something that you've done thousands and thousands of times in your life. However, sometimes you can obviously have more volatile environments. So an example of this, I've got a young niece who moves everything, puts things everywhere. If you were to one day sort of put your hand in and there was to be something unexpected, like a pineapple in that drawer, that's a highly unexpected cue that would be really surprising in a normal environment. But if, for example, my niece was staying for the whole weekend and I was to put my hand in that drawer the next day, it wouldn't be as expected that next time, would it? That surprise response would be reduced because the environment and my niece is quite volatile. However, once my niece has gone home and like 3 days later and I'm back in the working week, it's back to being a predictable environment. And so when you put your hands in, you don't predict that there could be a pineapple in there. You adjust your predictions, you adjust the weighting of your predictions again so that you're interacting in an adaptive way. And so that sort of hopefully starts to answer your second question there, that if you're autistic people, as Rebecca Lawson put it in that paper I talked about, if autistic people are constantly seeing the world as a little bit uncertain, as a little bit volatile, then you're less surprised by these unexpected events. But then actually the majority of putting your hands on the sock drawer, predictions are effective, expectations are effective, and you need to scale the sort of predictability and the precision of your expectations according to that stability that exists within the environment. However, autistic people would maybe, according to the hypothesis, would constantly sort of interact as if your niece is staying and you're constantly maybe less sure or more surprised by even expected cues. Does that answer your question there?
Well, kind of. I mean, I don't want to take too long over it, but shouldn't they then still do better in your more volatile condition than in your more stable condition?
So if we go to the volatile condition, what neurotypical participants have shown in these sort of tasks is that obviously the probabilities are changing over time, but that neurotypical participants are really adaptive and they're able to scale the predictions according to those changing probabilities. And so crucially, in a stable environment, they're able to adjust to the fact that they'll use prior expectations based on a lot of trials, for example, whereas in the volatile environment, they will be able to detect that the environment has changed and they will be able to adjust their predictions accordingly. If you're constantly seeing things as maybe surprising or unexpected, your ability to detect that that environment is changing becomes much more difficult. And so being able to detect what's just natural noise in an environment from an actual change in the environment would become much more challenging.
Right, okay, yeah.
Is that right? Thank you.
Thanks very much. So you showed that prediction in interaction with objects, so these kinds of orienting type tasks, is basically okay often in autism. But one feature that is seen in many people with autism is so-called stimming. So these are repetitive, somewhat stereotyped movements, sometimes flapping of the hands. Not every person with autism shows this, but it's relatively common. And I think it's not well understood, but one explanation that's been advanced for stimming, why do they produce this motor behavior, is because it's predictable, because it is something which allows them to generate a structured series of inputs. So I know you haven't talked about stimming, but it at least is worth thinking about as being an unusual, I don't know, perhaps reliance on prediction or interest in prediction. And I just wondered if you could comment on these self-generated movements as opposed to object interaction movements.
Yeah, so that's something that has been discussed in some of those more recent, very much that exact idea has been put forward. So some of the sort of active inference models, when we start to look at the application of predictions in action, this idea of stimming movements is something that is predictable, and you're sort of reducing uncertainty from the world around you by doing things that are predictable. So you're actively affecting the environmental, the sensory inputs that are coming in by sort of creating things that you know. So yeah, that has been something that has been proposed in some of the recent work. Rebecca Lawson's theory does address it. There's also been some really good work by Colin Palmer recently that has specifically looked at that.
Could I just come back briefly? I'm not an expert in active inference theory, but I mean, you know the so-called dark room argument, that if you're really trying to predict all of your inputs, the thing that you should do is go and sit in a dark room, and then you can be pretty sure that there won't be any unpredicted or unpleasant inputs. So I think the problem with an active inference theory of these self-generated movements is it doesn't really explain why it's better to move than not to move at all, right? So if you really want to predict the state of your body, it's best not to move it. So I'm not entirely happy that explanation solves the problem of these self-generated movements. But
yeah, and that's a really good point. I definitely am not going to argue one way or another. However, the theory that's being explained, the theory that's been put forward there to argue why there's differences, particularly between individuals, but also inconsistencies, I guess, in behaviour, has been argued that. One thing that's commonly reported in autistic people, we said like the best thing to do in some ways is not to move or not to sort of change things. Well, you think of fixated interests in autistic individuals, this idea of becoming very, very fixated on certain things. That has been suggested to be a hypothesis that can explain that. So yeah, there are some ideas that are being suggested that sort of say sometimes you don't see those differences, but when an environment is uncertain and unpredictable, stimming could be a way to add an element of predictability to it. But yeah, no, that's definitely a good evaluation point as well.
It's a very nice talk, thank you. One question again, which is kind of a bit wider, but it's something that I increasingly worry about in some of our autism studies, and my lab has done this as well. We tend to study only the pretty able adults with autism who can come into the lab and sign a consent form and, take part in all of these things. And I worry sometimes what we can say about the much broader population of people with autism who maybe aren't able to come into our lab studies or take part in this. Do you think these effects are generalised across the whole autistic population, or are we looking just at this subsample who are able to come into the lab?
No, absolutely. What you've said there is a really sort of valid limitation of a lot of the work we've done. We did see, from doing a sort of action-based task that was quite naturalistic, and I alluded to like the VR side of things, we did see that lots of participants came in with lots of different needs. We were able to conduct some testing on participants, for example, who are non-verbal, participants who relatively rarely would leave the house, were able to come in with a carer and able to do it quickly, and the virtual reality did seem to be quite an inclusive and accessible way of doing this research, which was a really nice sort of side effect, if you like, of the methodologies that we were using. But that's definitely a really important point. And I also want to say, without slating my work too much here, but that actually also a lot of autistic people have other co-occurring difficulties. And for the purpose, because we had to specifically focus on this idea of sensory motor difficulties in autism, we often had to exclude participants if participants came in and they had lots of other difficulties or co-occurring disorders, we wouldn't have been able to include them in the analysis for some of these tests. And actually moving forward, it's going to be really important to address the sort of broader neurodivergent community there.
Thank you. Thanks, Tom. Lovely talk. I just wanted to follow up on the first question, because you said that autistic people perform differently in the volatile environment, because having this kind of generally high expectation of volatility makes it hard for them to adapt to those kind of changing probabilities in the volatile environment. And therefore, they can't make good predictions in the volatile environment. And in the final experiment, you gave them the probabilities. So shouldn't that have sort of wiped out the difficulty that they were having?
Yeah, so that was the sort of rationale for providing these explicit cues, right? There's a sort of body of evidence that suggests autistic people may be unable to accurately track these probabilities over time, and so therefore we thought if we provided the explicit probabilities that that we might be able to alleviate some of these difficulties. It's important to say that we were providing sort of probability-based information, so we weren't saying the next ball is going to be a bouncy ball, the next ball is going to be a normal ball. We still had a level of ambiguity to it. So we were saying the probabilities of these were at a certain level. And so actually, if, for example, someone went up to a new game level and it said that they were likely to get lots of bouncy balls, but the first trial at that game level was a normal ball, if you're being sort of hyper-reactive to unpredictable things and you're seeing the world as constantly changeable, then that next trial you might already disregard those explicit cues and you might be biased by that recent sensory event. So you might be biased by that normal ball that's just occurred. That's where I haven't wanted to go into the sort of like mechanistic basis too much there, but that's where our data does support some of these claims by Rebecca Lawson's group about sort of differences in neuromodulation. So rather than it being differences in implicit learning what's more or less likely, autistic individuals are able to track what's more or less likely, but the sort of weighting that is given to these prediction errors is maybe atypical over time. So that's what our data appears to suggest. Does that answer the question right?
Okay, I think we should thank Tom again for a terrific talk.